A message from the dawn of time is reaching us now. This ancient light from the universe's first stars has traveled for billions of years, a cosmic fossil holding our deepest origins. By the end of this, you will understand how this primordial glow can fundamentally reshape our view of the cosmos and our own place within it. We will journey to the edge of observable reality, where the first flickers of starlight still shine. What does it mean to witness the birth of everything? That initial darkness was not an empty void but a cosmic womb, a vast sea of pristine gas waiting for a spark. For millions of years, the universe was a silent, opaque fog, with no light able to travel freely through it. Then came the cosmic dawn. The first stars did not just flicker on like candles. They erupted into existence, colossal engines of fusion known as population 3 stars. Think of our sun, then imagine a star hundreds of times more massive, burning with a brilliant blue-white intensity and living a short, spectacular life. These were the true pioneers, and their light was unlike anything that followed. It was a pure, intense ultraviolet radiation that began to transform the very fog that had shrouded the cosmos, a process called reionization. This was the moment the universe became transparent, the moment the lights truly came on. To witness this event, we cannot simply point a telescope and look. The light from that dawn has been stretched and transformed by its epic journey across time and space. We need a different kind of eye to see it. Each photon from that cosmic dawn is a messenger, a tiny packet of energy that has been on an unimaginable journey. These particles of light are the ultimate time travelers. They carry within them a perfect snapshot of the universe as it was when they first sprang into existence, a fingerprint of the cosmos in its infancy. But their journey has fundamentally changed them. The universe has expanded enormously since they began their voyage, and this expansion has stretched the very fabric of space, and with it, the light traveling through it. That once brilliant, searing ultraviolet radiation from the first stars has been cooled and stretched into a much gentler glow. We now detect it as microwave radiation, a faint, cold whisper all around us. This is the cosmic microwave background, the afterglow of creation itself. These photons are the most ancient things you can ever see, silent witnesses to everything. They have flown past the formation of the very first galaxies, through the birth and transition of countless stars, and watched as the great cosmic web of clusters and superclusters slowly assembled itself. To understand their message, we must learn to read their subtle language. Scientists do not just measure the simple temperature of this background glow. They look for incredibly tiny variations in it, minute-hot and cold spots that are like cosmic hieroglyphics. They study its polarization, a specific directionality imprinted on the light by the earliest cosmic events. Each fluctuation, each subtle pattern, is a chapter in the universe's autobiography, telling us about the distribution of matter, the strength of gravitational waves in the primordial universe, and the very seeds from which all structure grew. To decipher this ancient text, we cannot use ordinary tools. We need instruments of almost magical sensitivity, machines that can listen to the faintest echoes from the edge of time itself. Earth's atmosphere, a protective blanket that gives us life, can be a frustrating veil for astronomers. It blurs and distorts the very ancient light we seek, that faint cosmic whisper from the dawn of time. To truly listen, we had to rise above it. This was the visionary purpose behind missions like the Planck satellite, a technological marvel sent to a quiet gravitational oasis a million miles from Earth. From that pristine vantage point, far from our planet's atmospheric shimmer and radio noise, Planck could finally observe the universe's oldest light with breathtaking clarity. Its mission was to map the cosmic microwave background in exquisite detail, not as a uniform glow, but as a tapestry of the most minute variations. These tiny fluctuations, mere millionths of a degree difference in temperature, are everything. They are the preserved imprints of the earliest density variations in the cosmos, the foundational seeds from which everything we see eventually grew. Think of it like looking at the surface of a calm lake and being able to read, in the subtlest of ripples, the entire history of the winds that shaped it. Planck's map is that for the universe, a foundational picture of cosmic structure. Yet this raw map is not a simple photograph we can immediately understand. It is an encoded message, a complex dataset that demands translation. Unlocking its secrets requires another kind of tool altogether, the power of theoretical models and computer simulations that can rewind the tape of the universe, testing which initial conditions ultimately lead to the cosmic story we see written in the light. We have the grand cosmic map from Planck, but a map is only one piece of the story. To understand the timeline of that first dawn, we need a second, equally powerful tool. This is the science of spectroscopy, the art of reading the subtle fingerprints that matter leaves on light. Imagine sunlight passing through a stained glass window, its colors transformed. Now replace that window with a cloud of primordial gas at the edge of the observable universe, and the sunlight with the brilliant beacon of a quasar. As this quasar's light journeys for billions of years toward us, it passes through these ancient clouds of neutral hydrogen gas. This gas does not let all the light pass through unchanged. It absorbs very specific colors, leaving behind a unique pattern of dark lines in the quasar's spectrum, like a barcode from the dawn of time. By reading this barcode with incredibly powerful spectrographs on telescopes like the Keck Observatory or the Very Large Telescope, astronomers can detect the faint imprint of that hydrogen. They can see how this absorption pattern changes over cosmic time, revealing the precise moment when the first starlight began to transform that hydrogen. This is how we measure the timeline of cosmic reionization, that great transition from a foggy universe to a transparent one. It is a completely independent line of evidence, a stopwatch for the cosmic dawn that confirms and refines the story told by the ancient microwave light. The true power emerges when we bring these two tools together. The cosmic microwave background gives us the blueprint of the infant universe, while the spectroscopic data gives us the timeline of its first great awakening. One tells us about the initial conditions, the other about the dramatic events that followed. Combining them is like having both the birth certificate and the baby book of the cosmos, allowing us to build a single, coherent, and breathtakingly detailed picture of our deepest origins. This great transformation, the Reionization Epoch, was the universe's true awakening. For several 100 million years, a cosmic shift unfolded silently across the vast expanse. On one side was the primordial fog, a thick veil of neutral hydrogen gas that had cloaked the cosmos in darkness. On the other was the new light, the fierce ultraviolet radiation blazing from the first stars and galaxies. This was not a gentle sunrise but a slow, persistent clearing of the cosmic mist. Each photon of that early starlight played a part in this change, encountering a hydrogen atom and altering its state, transforming the neutral gas into a transparent, ionized plasma. The universe was fundamentally rewiring its own structure, lifting the veil so that light could finally travel freely across the cosmos for the very first time. We see the echoes of this profound transition etched into the ancient light we have been following. The cosmic microwave background radiation, that faint whisper from the beginning, carries the imprint of this event in its polarization. This specific directionality in the light is a preserved record of the last time those ancient photons scattered off free electrons during reionization. By reading these subtle patterns, scientists can peer back and estimate when this great clearing began and how long it endured. It is like finding a time stamp on the universe's birth certificate, a direct glimpse into the vibrant activity of the first luminous objects. This evidence points us toward the ultimate prize, the specific search for the very first stellar objects themselves. What did these cosmic pioneers actually look like, and how could we ever hope to find their individual signatures after all this time? These first stars, known as Population 3, are the ultimate cosmic pioneers. They are the foundational giants of our universe, yet we have never directly seen one. They are the holy grail for astronomers, a theoretical prediction that sits at the very heart of our origin story. The reason they are so elusive is that they were made of only the simplest ingredients, pure hydrogen and helium, forged in the Big Bang itself. There were no heavier elements like carbon or oxygen in their composition. This elemental purity made them unlike any stars we see today. It forced them to form as true behemoths, hundreds of times more massive than our own sun. Such immense size meant they lived fast and transitioned quickly, burning with a ferocious blue-white intensity for only a few million years before reaching spectacular conclusions. Their final moments were not quiet fades but colossal events, supernova of unimaginable power that seeded the cosmos with the first heavy elements, the very stuff that would later form planets and life. The light from these events is so ancient and has been stretched so far by the expanding universe that it is now woven deep within a faint, all-pervasive glow called the cosmic infrared background. It is a whisper lost in a cosmic chorus, so how do we find a pioneer? We look for its shadow, its echo, its impact on the world. Our best hope lies with a new generation of cosmic observatories, like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope. These are not merely telescopes, they are time machines. Their incredible sensitivity to infrared light allows them to peer back further than any instrument before. They will not likely see a single, pristine Population 3 star shining in the darkness. Instead, they will hunt for the indirect signatures these stars left behind. They might detect the unique chemical fingerprint of a supernova remnant, a cloud of gas enriched solely by the event of one of these first stars. Or they might observe the way these stars' intense radiation altered the pockets of primordial gas around them, leaving a distinct imprint on the light from even more distant objects. Finding even one clear piece of evidence would be a monumental discovery. It would confirm a critical chapter in our cosmic model, the moment when the universe began to forge the elements of life. Furthermore, their existence is inextricably tied to the birth of the very first galaxies. Did these colossal stars form alone, or did they act as the gravitational anchors, the seeds around which the earliest proto-galaxies began to clump and coalesce? The hunt for these stellar pioneers is really a hunt for our own cosmic ancestry, a search for the moment the universe began to build itself into the complex and structured place we call home. These stellar giants were the architects of the cosmos we know. Their immense gravity acted as a cosmic glue, pulling together vast clouds of pristine gas to form the very first proto-galaxies, the faint, primordial ancestors of majestic spirals like our Milky Way. This was not a solitary construction project. The life cycles of these first stars directly shaped the material from which their galactic homes were built. Their fierce ultraviolet radiation pushed on the surrounding gas, sculpting it and influencing how it could collapse. And when their short, brilliant lives ended in spectacular final events, they did more than just vanish. They became cosmic fertilizers, seeding the void with the first sprinklings of heavy elements, the carbon, oxygen, and iron that had been forged in their cores. This enrichment was a fundamental turning point. It transformed the universe from a simple place of hydrogen and helium into a complex chemical environment, paving the way for a second generation of stars. These new stars were different, born from gas that was already enriched with material from earlier generations. They could form with a wider range of sizes, and crucially, they could form rocky planets. The ancient light we detect today, that faint microwave whisper, carries the integrated history of this entire transformative process. It holds the combined glow of those first stars, the ionization from their radiation, and the echoes of the structures they helped build. To decode this complex story, astronomers create incredibly sophisticated computer simulations. These are virtual universes born from the laws of physics, where they can watch as digital particles of gas collapse under gravity, form simulated first stars, and release material to enrich the cosmic environment. The true test comes when they compare these virtual universes to the real one, matching the simulated patterns of ancient light against the subtle fluctuations observed by telescopes like Planck. This creates a powerful feedback loop. If the simulation matches reality, it confirms our understanding. If it does not, it encourages us to refine our theories about how those first stars and galaxies actually formed. This intricate dance between the birth of stars and the assembly of galaxies did more than just create isolated islands of light. It set the rhythm for the universe's large-scale structure, determining where the great cosmic web of filaments and voids would ultimately form. This ancient light does more than whisper a story. It reveals a hidden architecture. Those subtle hot and cold spots in the cosmic microwave background are a direct imprint of the universe's underlying skeleton, a cosmic web of dark matter and gas that spans the entire cosmos. Think of it like holding a sheet of paper up to a light and seeing the faint, fibrous structure within. The cosmic microwave background is that backlight, and the patterns we see are the shadows of the earliest seeds of all structure. Where the light is slightly warmer, it marks a region of the infant universe that was just a tiny bit denser, a gravitational well where dark matter and gas had already begun to pool. These over-dense regions were the cradles, the destined locations where the very first galaxies would eventually ignite and grow. By meticulously analyzing these patterns, cosmologists can essentially rewind the clock and produce a three-dimensional map of how all matter, both visible and dark, was distributed at the very beginning. This is our most fundamental blueprint for reality. We can then run the simulation forward, watching as gravity pulls this matter into the vast filaments and nodes of the cosmic web we observe today, and as the mysterious force of dark energy later begins to push it apart. This allows us to test our most fundamental theories of physics on a canvas that spans the entire observable universe. The precise nature of these patterns, their size and distribution, acts as a strict test for the laws of gravity and the properties of dark energy. It asks a profound question: do the rules of physics as we understand them here and now hold true across 14 billion years of cosmic evolution? Any tiny deviation in what we observe from what our models predict could signal a revolution, a hint that our understanding of gravity itself might be incomplete, or that dark energy behaves in ways we have not yet dreamed. This faint glow is not just a relic, it is an active laboratory for the most extreme physics, a window into the very laws that govern existence. These subtle patterns in the ancient light are a direct portal to the most extreme physics imaginable. The early universe was a natural laboratory of incredible energy, a place where conditions were so intense and dense that they cannot be recreated in any facility on Earth. The statistics of those faint hot and cold spots in the cosmic microwave background, their specific sizes and distribution, are not random. They are a preserved record of the universe's earliest moments, potentially holding clues to a brief but spectacular event known as cosmic inflation. This was a period of rapid expansion that occurred in the first fraction of a second after the Big Bang, smoothing and stretching the infant cosmos to set the stage for everything that followed. Think of blowing up a balloon with a microscopic pattern painted on it. As the balloon inflates, that tiny pattern is stretched across its entire vast surface. The fluctuations we see in the ancient light are that stretched pattern magnified to a cosmic scale. By studying their precise statistical properties, we are essentially reading the initial conditions written by inflation itself. But there is an even more profound signature we are hunting for, one hidden not in the temperature, but in the very twist and sway of the light itself. This is the quest to measure the specific polarization patterns imprinted by primordial gravitational waves. These are not waves in water or air, but ripples in the fabric of space-time itself, vibrations left over from the dynamic birth of the cosmos. Their detection would be a monumental breakthrough, a direct glimpse into an era when gravity itself behaved as a quantum force. Finding their faint whisper in the polarization of the cosmic microwave background would be powerful evidence for theories that attempt to unify the world of the very large, governed by gravity, with the world of the very small, ruled by quantum mechanics. It connects the grand architecture of the cosmic web directly to the frenetic dance of particles at the smallest possible scale. This ancient light allows us to ask the most fundamental questions about the nature of reality, questions about what happened at the very beginning and what the true underlying laws of the universe really are. The answers are not written in a book but coded into the cool, faint glow that has traveled since the dawn of time. This faint cosmic whisper from the dawn of time does not reach us in pristine silence. It arrives as one quiet voice in a roaring cosmic symphony, and our own galactic home is one of the loudest instruments in that orchestra. The Milky Way glows with its own powerful microwave light, a brilliant foreground that can easily overwhelm the ancient signal we seek. This glow comes from two main sources. First, there is synchrotron radiation, a type of light generated by high-energy electrons spiraling at nearly the speed of light through the galaxy's magnetic fields. Then there is the thermal emission from vast clouds of interstellar dust, gently warmed by starlight and re-radiating that energy in the microwave part of the spectrum. Beyond our galaxy, other sources add to the chorus, from distant galaxies to galaxy clusters. All of this creates a rich tapestry of modern cosmic noise that lies directly on top of the primordial signal. The challenge for astronomers is like trying to hear a single, faint violin playing from miles away while standing in the front row of a rock concert. To isolate that one ancient instrument, they must perform a feat of cosmic subtraction. They use multi-frequency observations, mapping the sky at many different microwave wavelengths. Each type of foreground emission has its own distinct spectral signature, its own unique color in this invisible light. By carefully measuring how the sky looks at each frequency, astronomers can build a detailed model of the foreground symphony. They then use complex statistical techniques to meticulously subtract that model from the total signal. What remains, they hope, is the pure, pristine sound of the cosmic dawn. This process is incredibly delicate. Any small error, any misstep in modeling the foregrounds can leave behind artificial patterns or erase real ones, leading to a complete reinterpretation of the primordial signal. It is a reminder that our view of the very beginning is always filtered through the vibrant, complex, and sometimes overwhelmingly bright universe of the present, pushing our day to analysis to its absolute limits. Decoding this ancient light requires more than just powerful telescopes. It demands a new kind of laboratory, one that can hold an entire universe inside it. Researchers turn to the world's most powerful supercomputers, running colossal programs known as cosmological simulations. These are not simple animations. They are intricate digital universes born from the fundamental laws of physics. Scientists define a starting point, a smooth, hot soup of matter and energy that matches the conditions seen in the cosmic microwave background. They then set the rules, the equations for gravity, fluid dynamics, and the formation of dark matter halos. With a digital command, they press play, and the simulation begins its journey across billions of virtual years. They watch as gravity pulls matter into a cosmic web of filaments, as gas cools and collapses to form the first stars, and as those stars explode to seed space with the elements for future generations. The goal is to create a synthetic history of everything, a parallel universe born from our best theories. The true test comes when they compare their creation to our own reality. They generate synthetic maps of the cosmic microwave background from their simulation, complete with their own patterns of hot and cold spots. They also create artificial observations of the light from the first stars and galaxies. They then hold these digital predictions up against the real data collected by instruments like the Planck satellite and the James Webb Space Telescope. Does the simulated ancient light match the subtle fluctuations we actually observe? Does the timeline of star formation in the virtual universe align with the evidence from quasar spectra? This iterative process is a continuous conversation between theory and observation. When the simulation matches reality, it powerfully confirms our understanding of cosmic evolution. When it does not, it reveals a flaw in our assumptions, pushing us to refine our models of how the first stars ignited or how dark energy behaves. These digital universes are not just for show. They are essential tools, allowing us to run experiments on cosmic scales and finally translate the faint whispers from the dawn of time into a coherent story of our own existence. The faint patterns we see today are only the beginning of the story. To push beyond our current limits, a new generation of cosmic observatories is being designed, instruments of almost unimaginable sensitivity. The International Lightbird satellite mission, now in development, represents a monumental leap forward. Its singular goal is to measure the polarization of the cosmic microwave background with a precision we have never before achieved. It will hunt for the specific twist in that ancient light, the unique signature that could only have been imprinted by primordial gravitational waves from the universe's earliest moments. This is not just an incremental improvement, it is a quest for a signal that would fundamentally reshape our understanding of physics. Meanwhile, on the high, dry plateaus of Chile and Antarctica, colossal ground-based projects are taking shape. The Simons Observatory and the even more ambitious CMB-S4 project will deploy vast arrays of ultra-sensitive telescopes. These are not single instruments but coordinated armies of detectors, working in unison to map the faint microwave sky in exquisitely fine detail. They will scan the heavens, filtering out the foreground noise from our own galaxy with unprecedented clarity, to reveal the underlying primordial tapestry in sharper focus than ever before. Each of these endeavors is like adding a new, more powerful lens to our cosmic microscope, allowing us to see the subtle brushstrokes in the universe's first portrait. Their success hinges on a truly global effort, a testament to humanity's shared curiosity. Scientists and engineers from dozens of countries are collaborating, pooling knowledge and resources in a sustained investment to answer our most profound questions. These missions promise to peel back another layer of the cosmic onion, bringing us closer than we have ever been to directly witnessing the moment the very first starlight emerged across the early cosmos. This ancient light carries a message not just about how the universe began, but why it turned out this particular way. The specific pattern of hot and cold spots, those tiny seeds for all future structure, were precisely tuned. Had those initial fluctuations been even slightly stronger, matter would have collapsed too violently, forming only enormous singularities. Had they been any weaker, gravity would not have been able to pull matter together at all, leaving the cosmos a forever featureless sea of gas. We find ourselves in a universe that struck a perfect balance, one where galaxies, stars, and ultimately planets like our own could coalesce. This realization brings us to a profound and deeply personal question, the anthropic principle. Why does the universe appear so finely tuned for the existence of life? The investigation of this primordial glow is far more than a technical exercise in cosmology. It is a quest to understand if the fundamental constants of nature, the very rules of reality, are the only ones possible, or if we simply live in one rare universe among a vast multiverse where such life-friendly conditions are met. This connects the impersonal, cosmic scale of the microwave background directly to the intimate reality of our own planet. The same physical laws that govern the formation of the first stars also orchestrated the chemistry that allows us to exist and to ponder our own origins. When we map the subtle variations in that ancient light, we are not just reading a history book. We are uncovering the foundational settings that made our own story possible, exploring the deepest connection between the vast cosmos and the delicate spark of life. The story of a first light piercing an eternal darkness is one of humanity's oldest narratives. Long before telescopes or satellites, our ancestors gathered under the night sky and told tales of creation, of a cosmos born from a formless void. The Babylonian Enuma Elish describes God's shaping order from chaotic waters. The opening of Genesis proclaims, "Let there be light," across the deep. Indigenous cultures from the Americas to Australia speak of ancestral beings bringing the sun and stars into being. These myths were not primitive science but profound attempts to answer the most fundamental questions, to find meaning and purpose in the grand expanse. They represent the universal human drive to explain our origins. Today, we are telling a new version of that same story, but our characters are not gods and monsters. They are hydrogen clouds and gravitational collapse. Our narrative is not written on clay tablets, but in the faint microwave whisper of the cosmic microwave background. This ancient light from the first stars is our scientific creation myth, a tangible, observable connection to the actual beginning of everything we know. The bridge between the mythological first light and the astrophysical one is not a contradiction, it is a continuation. It reveals that our quest to understand where we come from is a constant thread running through human history, from the first stories told around a fire to the most advanced space observatories. This cosmic connection enriches our appreciation, reminding us that science does not strip the universe of wonder. It simply gives us a new language with which to express it. The awe our ancestors felt gazing at the stars is the very same awe that drives physicists to decode the universe's first light. We are still telling the story of the dawn, only now we are beginning to understand its true scale. This search for cosmic origins is a story that belongs to everyone. The journey to decode the universe's first light is no longer a task for a small group of specialists working in isolation. It has blossomed into a global, collective endeavor, inviting public participation on an unprecedented scale. Online platforms such as Zooniverse have opened a digital doorway for anyone with an internet connection and a spark of curiosity. Here, citizen scientists from all walks of life can sift through vast collections of deep-field images from the world's most powerful telescopes. They help to identify and classify distant, faint galaxies, many of which are seen as they were in the universe's youth. This is not a passive activity, it is active discovery. The human brain's remarkable pattern recognition skills can sometimes spot subtle features that even sophisticated algorithms might miss. Every classification made by a volunteer is a small but vital contribution, helping professional astronomers to map the early cosmos and understand how the first structures assembled. This data is indeed a treasure trove, and now thousands of hands are helping to sift through it, turning raw information into profound knowledge. But the engagement does not stop at the computer screen. The grand narrative of the cosmic dawn is being brought to life in immersive planetarium shows and stunning documentaries. These experiences translate complex data into a sensory spectacle, allowing audiences to feel as if they are flying through the cosmic web or witnessing the ignition of the first stars. They make the abstract tangible, transforming faint microwave signals and theoretical models into a visual and emotional journey. This accessibility is crucial, for it plants seeds of inspiration in young minds, potentially nurturing the next generation of cosmologists, engineers, and explorers. By pulling back the curtain on this profound research, we foster a deep, shared appreciation for fundamental science. It reminds us that the quest to understand our place in the cosmos is a fundamental part of the human experience, a direct expression of our innate curiosity that connects us all across time and culture. This pursuit of the universe's first light has quietly seeded a revolution in our own world. The technological challenges of capturing a faint cosmic whisper have demanded engineering solutions that now resonate far beyond astronomy. Consider the quest to build detectors sensitive enough to measure the subtle patterns in the cosmic microwave background. This drove the creation of superconducting materials and incredibly precise sensors that operate at a fraction of a degree above absolute zero. This same core technology now forms the heart of modern magnetic resonance imaging machines, the MRI scanners found in hospitals worldwide. The ability to detect incredibly faint radio frequency signals from deep space directly enhanced our capacity to map the delicate structures of the human brain, transforming medical diagnosis. Even the sophisticated cooling systems developed for observatories like Planck have advanced the entire field of low-temperature physics, leading to more efficient and powerful superconducting magnets and new approaches to refrigeration. The immense flow of information from these cosmic missions presented another creative challenge. The detailed maps of the sky contained more raw data than could be easily sent back to our planet. Scientists were inspired to pioneer new, highly efficient data compression methods to handle this cosmological bounty. These very algorithms are now woven into the fabric of our digital world, improving everything from online video streaming to the management of large-scale financial and telecommunications networks. This pattern is a powerful reminder that investing in fundamental, curiosity-driven science rarely yields just a single answer. The journey to understand a faint glow from the dawn of time can spin off a cascade of innovation, delivering tangible benefits that touch our lives in the hospital, the home, and the global marketplace. It demonstrates that the value of asking profound questions about the cosmos is not confined to the abstract. It echoes back to us, shaping our technology and improving our world in deeply practical and often unexpected ways. The sheer volume of information flowing from these cosmic observatories is almost beyond comprehension. We are no longer dealing with simple datasets, but with a true deluge of cosmic information. A single mission like Planck collected terabytes of data, a number that already feels immense. Yet the next generation of telescopes will generate thousands of times more, reaching into the realm of petabytes. To put that in perspective, a petabyte of data could hold over 10 years of high-definition video. This is the new reality of cosmology, a field now defined by its ability to manage an ocean of digital information. Handling this flow requires more than just bigger storage. It demands an advanced computing infrastructure with vast server farms and high-speed networks designed to process and store these colossal cosmic maps. But the real shift lies in how we analyze this information. Scientists are now training sophisticated machine learning systems to sift through these immense datasets, teaching computers to recognize the subtle statistical patterns and faint signals that human eyes would simply miss. These systems act like intelligent sieves, filtering out the noise of the modern universe to isolate the quiet whisper of the ancient one. The ability to draw a single, profound insight from a petabyte of raw numbers is becoming as crucial as building the telescope itself. This monumental task is too vast for any single nation or institution to manage alone. It calls for a new level of global partnership, where shared data and collaborative analysis become the only path forward in our quest to understand the dawn of time. This monumental quest to understand our cosmic origins has always been a global effort. No single nation or institution could ever shoulder the immense technological and intellectual burden alone. The Planck satellite, which gave us our most detailed map of the ancient universe, was a flagship mission of the European Space Agency. Yet its success was powered by the collective brainpower of scientists and engineers from dozens of countries, all contributing their unique expertise. This model of international partnership is the new standard. The upcoming Cosmic Microwave Background Stage 4 project, a ground-based observatory of unprecedented scale, is a formal partnership between the United States and a wide consortium of international contributors from Chile to Europe and beyond. This is not just about sharing costs, it is about sharing perspectives. By pooling resources and diverse ways of thinking, we accelerate discovery, avoiding duplicated efforts and blind alleys. The profound insights we gain into the nature of reality do not belong to one country. They are a shared human achievement. In an age often defined by division, this quiet, persistent cooperation among nations stands as a powerful testament to what our species can accomplish when we unite in curiosity. The knowledge we gather from the ancient light fundamentally shapes a unified cosmic perspective, reminding us that we all inhabit the same fragile planet under the same vast, ancient sky. This cosmic horizon presents a boundary as real as any cliff edge, a final frontier beyond which our most powerful instruments cannot peer. We call this limit the surface of last scattering, a moment roughly 380,000 years after the universe began. Before this pivotal era, the cosmos was a searing, churning plasma, far too dense for light to travel freely. Photons were trapped, constantly bouncing off a thick soup of particles, rendering the entire universe an impenetrable, glowing fog. We simply cannot receive light from any time before this wall of opacity. The cosmic microwave background is that wall, the oldest snapshot we will ever have. It is the moment the universe cooled just enough for atoms to form, allowing light to finally escape and begin its long journey across the ages. Everything we observe about the first stars and galaxies comes to us from a time long after this great release. They are the very first structures to emerge from the darkness, appearing on the farthest shore of our observable universe. This horizon defines the ultimate limit of our direct vision, a fundamental barrier written into the laws of physics itself. Because we cannot see beyond it, we are forced to become cosmic detectives, piecing together the clues from that ancient light to reconstruct what must have happened in the deep, unseeable past. We rely on the subtle imprints left on the cosmic microwave background by events that occurred even earlier, in that first fleeting fraction of a second. This limitation does not halt our quest, it simply pushes our ingenuity to its absolute peak, inspiring a new era of theoretical exploration that reaches for the very beginning of time. Without direct observation, we must rely on the powerful predictions of theoretical physics. The standard model of cosmology provides our best framework, a set of mathematical rules that allow us to simulate the birth of those first stars. These models paint a portrait of stellar giants that were not only immense but also incredibly luminous, flooding the nascent cosmos with transformative ultraviolet light. Their lives were spectacularly brief, burning through their nuclear fuel in just a few million years. This fleeting existence suggests they may not have lived in isolation. Sophisticated simulations show these behemoths could have formed in tight-knit groups, as binary pairs or even multiple systems, orbiting each other in a brilliant, chaotic dance. Their spectacular final acts are just as consequential as their births. Theoretical models propose that when these stars reached the end of their life cycles, they did not simply fade away. Their immense gravity could have compressed them directly into the universe's first intermediate mass black holes. This is a profound speculation, as these primordial objects could have acted as the foundational seeds. Over billions of years, by drawing in vast amounts of gas and merging with one another, they might have grown into the supermassive black holes that now anchor the centers of galaxies, including our own Milky Way. These theoretical predictions are far from idle guesses. They are the essential maps that guide astronomers. They tell observers exactly what to look for in the faint infrared data from the James Webb Space Telescope, defining the specific chemical signatures or light patterns that would confirm these ideas. This dynamic interplay is the true engine of discovery. A theoretical prediction inspires a new observational strategy, and the resulting data, in turn, refines and reshapes the theory. It is a continuous, self-correcting conversation that slowly, methodically, turns our most educated speculations into confirmed knowledge about the dawn of time. There is a moment in this work that transcends every graph and calculation. It arrives quietly when you remember that the faint signal you are studying is not abstract data but ancient light. A photon that has been traveling since the dawn of time for nearly 14 billion years has just ended its immense journey against the sensor of a telescope you helped to build. In that instant, you are not merely an observer looking back. You are the universe meeting its own history, a direct recipient of a message sent when everything began. This realization carries a weight that no equation can fully capture, a profound humility that redefines your place in the cosmos. We are woven from the legacy of those first stars, our very atoms forged in their fiery hearts and spectacular final acts. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was once stardust, scattered across the void by those primordial giants. This is not a metaphor, it is our physical lineage. The same cosmic evolution that cleared the fog of the early universe and assembled the first galaxies also set in motion the intricate chain of events that led to a planet, to life, and to a species that could one day build a machine to catch that ancient light and understand its story. We are the universe becoming conscious of itself, a way for the cosmos to look back upon its own origins and contemplate its own existence. This emotional connection, this sense of awe, is not separate from the science. It is the fuel that powers the long nights and the relentless curiosity. It reminds us that in decoding the light from the first stars, we are ultimately searching for our own cosmic ancestry, listening for the faintest echoes of our own beginning. This cosmic story offers more than just answers, it provides a gateway to learning. The epic journey of ancient light from the first stars serves as a perfect classroom for the next generation, weaving together the fundamental laws of physics, astronomy, and chemistry into one unforgettable narrative. Instead of presenting these subjects as isolated facts, educators can use the mystery of the cosmic dawn to show how they are all deeply connected. Asking a student to investigate how the first stars forged the elements is far more engaging than simply memorizing the periodic table. It transforms abstract science into a grand detective story, one that naturally builds critical thinking as students weigh evidence, analyze data, and follow the clues left in the light. To make these colossal concepts tangible, interactive simulations are incredibly powerful tools. Imagine a student sitting at a computer, able to adjust the initial density of the primordial universe or the strength of gravity, and then pressing a button to watch a digital cosmos evolve before their eyes. They can see for themselves how tiny changes in the starting conditions lead to a universe without galaxies, or one that collapses back in on itself too quickly. This hands-on exploration makes the fine-tuning of our own universe vividly clear, turning a complex theoretical idea into a personal and impactful discovery. By investing in this kind of immersive education, we are not just filling minds with information, we are nurturing the innate curiosity that will drive future breakthroughs, ensuring that the children in classrooms today become the scientists and engineers who will one day build the next great observatory, asking questions about the cosmos we have not yet even learned to form. No single scientific field can solve this puzzle alone. This search for the universe's first light is a fundamentally interdisciplinary quest, a grand collaboration that spans the entire landscape of human knowledge. Astronomers map the ancient sky, but they rely on the foundational work of particle physicists, who use powerful accelerators to recreate the extreme conditions of the infant universe. Their models of the primordial soup of matter and energy provide the essential starting point for our entire cosmic story. Chemists contribute a crucial piece by decoding the process of nucleosynthesis, detailing how hydrogen and helium fused inside those first stellar furnaces to create the earliest heavier elements. They tell us what the first stars were made of and what they left behind. Then there are the computer scientists, the architects of our digital universes. They write the complex code and design the powerful algorithms that bring theoretical models to life, allowing us to run cosmic evolution in a box and test our ideas against the faint glow of the microwave background. Perhaps most surprisingly, this collaboration even extends to philosophers, who help us grapple with the profound implications of our discoveries. They explore the meaning of a finely tuned universe and the nature of existence itself, questions that arise directly from the data but stretch far beyond it. This fusion of disciplines is not just helpful, it is essential. A chemist's insight into molecular bonds can inform a model of early star formation. A computer scientist's new data compression technique can unlock a clearer view of the primordial signal. This synthesis of knowledge from wildly different fields creates a whole that is far greater than the sum of its parts, proving that our deepest questions about the cosmos demand every tool of inquiry we possess. The resources dedicated to cosmic exploration present a profound ethical question. We must ask how to balance this fundamental human drive for knowledge with the immediate and urgent needs of our world. It is a question of priority, of looking up at the stars while standing firmly on the Earth. Yet this is not a simple either-or proposition. The pursuit of cosmic understanding offers a powerful return on our investment, one that often pays dividends right here at home. The technological breakthroughs driven by this research, from medical imaging to data compression, directly benefit global society. More than that, the story told by the ancient light provides a perspective that is deeply needed. It reveals a planet without borders, a delicate world of interconnected life adrift in a vast cosmic ocean. This shared cosmic context can inspire a sense of global citizenship, gently encouraging cooperation over conflict by reminding us that we are all crew on the same small spacecraft. This does not diminish our earthly responsibilities, it reframes them. The goal is not to escape our world, but to understand it as part of a much larger whole, ensuring that our journey to the stars is guided by a deep and abiding wisdom for our only home. This journey through ancient light reveals a universe far grander than any single discovery. It connects the fiery birth of the first stars to the quiet glow of your screen, a continuous thread woven across 14 billion years. That faint cosmic whisper is more than a scientific dataset. It is our most direct link to the beginning of everything, a physical connection to the moment our cosmic story started. It has acted as a fundamental laboratory, testing the laws of physics on the largest possible scale and pushing our understanding of reality itself. Above all, it stands as a timeless source of inspiration, reminding us of our humble yet remarkable place in this vast cosmic tapestry. The quest to decode this message is a celebration of human curiosity, a global effort that spans disciplines and nations, all united by a simple, profound question. Where did we come from? As new telescopes and missions prepare to open their eyes to the sky, we are not reaching the end of this story. We are standing at the threshold of a new chapter, poised for revelations that will undoubtedly reshape our cosmic narrative once again. The next time you find yourself under a clear night sky, take a moment to simply look up. The starlight bathing your eyes is the living legacy of that first cosmic dawn, a story written in photons that began its journey long before our world was born. We would love to hear what part of this cosmic journey resonated most with you. Share your reflections in the comments, and if you want to continue exploring the universe's greatest mysteries, subscribe to join us on the next adventure.